So in this recording, that is going to be quite short, I'm going to show how to debug the Linux kernel boot process in ARM. What I'm going to be using here is a Yocto project build of the BeagleBoneblack, and I'm going to actually emulate it with a QEMU. And I can also show how to do it when you build like any kernel of your choice and build it with QEMU, or if we were like in a real classroom scenario and I would have device and hardware debugging probe, then I could show it like there also, but this is not the case right now. So this completes our x86 early setup and early boot kernel scenario. And essentially what I want to do is to just not go over all the details, just show you the exact same techniques. So this video is going to be quite short. So just to recap what we did in the previous video that I put on YouTube, then the x86 loading procedure, and I'm going to focus on 32-bit because it has less steps, but it's quite similar to 64-bit and very similar to every architecture, has two phases. It has one phase of real mode setup that is indicated by setup.elf under the boot directory, where its entire point is to make sure that the kernel that is being started in 16-bit mode can move to what is known in x86 as protected mode. So this particular part is completely not relevant in ARM. What is relevant is being done in the second part of x86 that starts from compressed folder, and there you have a file called compressed VM Linux, and I'm not going to rediscuss the structure of the images. I put videos on that also. Is that the idea is that you want to go ahead, your kernel is loaded somewhere, you want to copy it to a higher address so that you can extract the kernel in place. Then you're going to parse the extracted content that is going to be an ELF file, relocate the sections, and jump to a kernel starting point that is actually going to be under the kernel folder. So in x86 it's going to be kernel head, and you will see that in ARM it's going to be the same. Then at this point the objective is going to be to turn on paging or turn on the MMU. We're going to have such a function name in ARM, and eventually after initialization call start kernel, which is the init main kernel starting point that is architecture independent and so on. So this is what we're going to do at this part. So for the setup, on the left hand side I'm going to run QEMU, and just going to show you one little thing, like basically if I run it like without any parameters, okay, there was another device that was open, so I will close it. So what I want to show you is that what would happen if you run it without any parameter, then you're actually going to have like a fully working kernel. It emulates ARM, and now it runs init. And we're not going to talk about these phases. I talked about it enough, and I will talk about it enough. But at the end of it, you're going to have like your prompt, and we want to go and debug the early parts that are way before you even see the first message here, okay? So that's what we're going to do. We're going to run the exact same kernel, and which is here represented by some sort of drive, but we're going to actually run the kernel that we have, that is this guy. So we're going to run the kernel that is listed here under Yocto. And when it boots, we can actually see that this is like the kernel version that we have, and that uname-r says that it's 5420 Yocto standard. On the right hand side, we're going to actually invoke a debugger. So here I have my build directory in Yocto. I can show you later like how to actually interpret it, but if we want to look at the source, we have a link to the source, okay? So here it goes. So first thing I'm going to do is actually I'm going to go and run this. I'm going to disconnect from my device and I'm going to run it again. This time with the QEMU params. So if I give it -s, add it to the QEMU params, it means it's going to wait for a debugger. So I'm going to attach this debugger. So the debugger can be actually any GDB multi-arc, and I'm going to connect here to target remote 1234. So when I do that, as you can actually see in QEMU code, this is my entry point in this particular place, like in this particular emulation of this particular machine. And the reason for that is that this is what has been decided. Now this was the loading address right now, okay? Now if I go and disassemble it, let's go and look at some more instructions. Then I can see these 4 commands. Now here we see that we load into the program counter. This is essentially a jump. And we can see here that if we just like examine the memory of where we are now, we can see that this particular address, and in ARM when you see PC, actually there is like a prefetch, and if you're in debugger in a particular place and think that your PC is here, the real value of PC if you load into it is 2 instruction forward. So when I have this loading, then I'm actually going to go to this address, okay? So I'm going to go progress, and here's the jump, and there we are. We have here 8 NOPs, which is essentially the start of header.c, okay? So let's go ahead and look at it. So I will go in the second tab to the source directory, and I'm not going to talk about source code too much, and I'm actually not going to single step everything. I'm just going to go through like the same phases we saw in the x86. So if we go to ARM, actually the starting point is going to be boot compressed. Now under boot we have other things. DTS, here you're going to have the device tree blobs and the device tree sources, and you also have, if you want to build with bootp, you also have a couple of files here, like a linker script that says, hey, like this is where we start, and there is going to be like this underscore start, and these are the sections. This is not the subject. And init.rd that just includes another binary. A kernel that actually includes, check this out, arm boot z image, which is essentially, if you look like at the link, that's what we run like around QEMU. This is the file that we're looking at, the z image, and it includes it in the point kernel start. So if somebody, if the linker actually going to link these guys together, as it does, then we're going to, when we jump to kernel start, then this is what's going to be executed, okay? Whatever is the first instruction here. And then there is another file, init.s, that has this underscore start function, does all kind of things, okay? You're going to see like the tags, you're going to see things of where the device tree blob is loaded, if there is device tree blob, if there is init.rd, and so on and so forth. And then you'll have a branch to kernel start, which is what we saw a bit earlier. Now, I'm mentioning this actually just because we have like this branch and we have this z image, just so we see that a little bit of structure, but we did not build it. In order to build it, you need to do to build a bootp image, and I'm not doing that, okay? What I do care about is the entry point that we see in the debugger, which is this guy, these 8 knobs. So these 8 knobs are, you're going to see them under boot compressed and head.s. It's going to have rep of 8 knobs. So this is going to be repeat 7 times the knob command, and we have another knob. You can see here that here we have like the 8 knobs, and then we have a branch. Okay, so these are the repetitions, and we don't have like these things like here. We're not, this is the 8th one because we're not with config dump to kernel, and we have like the branch here to 1f. Okay, that's going to be somewhere here. Now let's go ahead, let's step through this. Now the first thing I may want is to actually have an output file out of it, so I'm going to take care of that. I'm going to quickly SSH to have another tab perhaps, so I'll pause for a second. So what we're going to do in order to have debugging symbols is we're going to first go to where arm boot is defined, and here we have under compressed, we have a VM Linux that if you look at like how VM Linux were created, you will see that head.o is indeed linked to it. And if we look like at addresses, yeah, we can just load head and everything will be okay. But if we like look at the addresses with obj dump, and this is the ARM obj dump, you need to have architecture dependent. Let's see of the different sections. So I'm going to do, for example, HW here to have a wide format, and W is going and H is for the sections of VM Linux. You can see some of these things like .txt and so on. Okay, so it starts like with VMA 0, and if we disassemble the file .txt, we can see these exact things. So if I go and load this file in the right place, then I can go ahead and actually have function names and symbol names. So that's what I'm going to do. So I'm going to add symbol file of arm boot compressed VM Linux, and I'm going to add them in my loading address that was 0x400 10,000. I'm going to give it yes, and now I actually have some more debugging information. So that's an important step, and I'm going to actually make it fast. I'm not going to talk about all the phases. I remind you that the important things here that are also done in x86 are going to be to relocate the kernel to higher address, extract the kernel, enable paging, enable the MMU, and then calling start kernel, where we will conclude. So you're expected to see in ARM, first of all, a lot of assembly, and you're expected to see a lot of work with enabling the caches, with disabling the caches, with flashing the caches. So these are going to be naturally in a lot of loops, and I'm just going to skip them. I will quickly single step them so that you will see. At some point I'll say important things, and for the most part I'm going to skip a lot of those things, okay? So that will not take hours. If it really interests somebody, if particular initializations are important for you, I can deliver a talk that is much more technical and much more in-depth about how to make things in ARM work. Okay? If you want to do things and you understand more or less how things work and know ARM assembly quite well, you need to go to the reference manual and see what kind of things need to do. Or you can reproduce what I'm doing now and look at the source code or disassemble single step yourself. This is the objective, to help you teach yourself by source, disassembling, and debugging. So comes a jump, and I'm just single stepping it, and there's like hypervisor stop, and soon enough we're going to have cache enabling. So cache on enables cache, and usually when we have cache function, there is going to be a call to a specific cache function that is going to have there are several architectures. So they're going to have their own characteristics and they're going to have their own functionalities. So you're going to see loops that do all these kind of things, cal, cache, fn, and so on. I'm just going to skip it, and then we'll see like something specific for the ARM v7. So in the ARM v7, you have mu cache on. If it was like another version, then you would see other things. Now we see calls to set up MMU. That makes a lot of sense. I'm going to step through them also. I'm actually going and doing some slow things. I'm doing single step instructions so that I can stop at like strategic places. Because sometimes if we just do like next instruction, then we will miss them. Okay. So setup MMU, we see that it takes like a lot of time. So if we just want to see, okay, where am I or what do I want to do, I can go ahead and like observe what is being like compared here. I can go to the code, to the source code itself, and see what is the situation here and what is like the loop and what I compare. But now I'm going to see that like there's actually like a testing, and I want to do it for registers, and I'm doing something, and then I compare values, and I say, okay, if they're not equal, I jump back here. I don't want to jump back, so I'm just going to put a temporary breakpoint after this one and jump forward. So this is setup MMU, and here we have a jump to where we were before, to the link register. So I'm back now at MU cache on of RM7, and after that I'm going to a function that we'll see several times that it's called restart. So restart is going to be called several times when interesting things happen with the MMU, okay, or with the caches. So I'm not going to go over it too much. So we're going to start instructions, and then there is a function that is very, very, very interesting for us. That is the DTB check done. It has to do with when we are done like parsing all kind of things and know like where, like if we have device tree blob and we also need like to relocate this, then where it is. But assume that everything is like one piece, okay? And this function just does something. So I'm going to single step here, and soon enough you're going to see something quite interesting. So we're getting there, and pay attention to these three commands. I skipped one of them accidentally. We have load multiple data bytes, we have store multiple data bytes, and we have comparison. Now look what's happening here. It's pretty much like the repeat command in x86. Then they did in one command that copied actually the kernel from the loading address to a higher address. It's exactly what's happening here. We have here 8 registers that we read into them whatever the memory wherever R6 is pointing. After that, R6 would be it's going to be decremented, okay? And what we're going to have is that these registers we're going to later store their contacts, okay, to the current index of R9. So we're going to read into them and then write into them, like 8 registers every time, okay? So 32 bytes of copying. What is the ending condition? The ending condition is going to be this CMP where R5 is equal R6. R6 is going to be progressing. Okay, so this is the second loop that we have. And if I look like at R5 and R6, I see here that these are the values. This is like the first of R5, and this is like R6. Okay, so we start like from the end and we copy like backwards, exactly like in the x86 case. So I could go and like step over them and step and step and step, but it is not necessary. So I'm going to go and break after the loop. And if I just go ahead, and my objective is not to jump back. Actually, jumping over the loop is supposed to be here. So I'm going to break here. And when I'm done, look at the values of R6 and R9, okay? So these are their values. So R6 points to this address, that if I look at it, it's right before restart, okay? And R9, if I look at its address now, then I basically see the exact same words, okay? If you look at the code, you will see the exact same code. If you look in the memory, you'll see the exact same hex numbers, okay? Because we relocated it. So at this place, we have this. We have R6 points to the where I started copying just before, and R9 points to where I started relocating to, okay? So I want to see what is the relocation offset. So I'm going to set reloc offset. I made up the name, you can do anything you want. And I'm going to set it to R9 minus R6. I accidentally before, instead of minus, I put equal. It was a typo. This is why I restarted it, okay? So now I'm going to see what is this value. And this is if I jump, when I jump to R9's address, it's going to be much later, I will no longer have the nice symbols here. So I could just load the symbol file again and add this relocation offset to it. So what we also do here, as you can see, we subtract them. So now R6 will be equal to the same value that I calculated. And we add this to the stack. So we're going to adjust our stack pointer to have like a nice and shiny environment. But we now going to clean the caches and do some cache activity. So once again, I'm going to step here and once again call cache function, and that's going to take quite a while. But one of the nice things that we'll see like that is that we can at some points actually get back, because we had like a branch or branch and link, and sometimes GDB will actually have the right context. So I'm just going to either skip it and do finish, or run a lot of this and like figure out where to jump to and so on. It will not take so long, but these ones, like the loops, will take. So I'm saying, okay, like where are we? What is like the current objective and who called us? So I can see that like at this particular point, this is not still good enough, because if I do like the left hand side, everything runs. So you need to be very careful about these things. So now we'll do it again properly. We can later on, I'll show you when, actually we'll have like the right stack format, and we'll be able to do it later on. Like we adjusted the stack, for example, but we did not adjust this, like we did not adjust like the addresses. We are not in the right address space. So here, what I'm going to do is rerun it, reconnect to the target, so I can just actually jump to where I were. It would be just fine. So let's do a temporary breakpoint on that. Continued, and then I'm like in the same place as before. Okay, so like even if you mess up, then everything is okay. It is these are the things that I want to demonstrate, but before I actually messed up because of a typo. This was like unintentional. I'm doing it live, okay? And I'm trying to keep it short. So here we can proceed. We can also like do next instructions. In order to do that, it's going to take some time, okay? So I'm going to just nicely skip it. So I'm going to now put a breakpoint in finished, and I'm going to put a breakpoint in hierarchical. And here I am at finished. So I'm going to pop registers. We have coprocessor routine. And now we have flash and we have DTB done, and look what's going to happen. So R0 is going to be this value, 410 EC708. Now this is much higher than this one. If you try to look at the instructions there, you will see that they're not recognized. Okay, so I can actually remember this relocation offset that we talked about earlier. Well, what we can do is add to it. So we can load the symbol files again, and instead of this value, we can actually go ahead and add reloc offset to it. Okay, this is a typo, and so if I do add symbol file again, and this time give it this address, then now I will of course lose my addresses. I actually didn't delete the previous one, so I should delete the previous one, but they're 4 enough, so GDB will be okay with it. And then I could see that we are in restart. We have won't override here, and down below we can see this couple of functions that looks quite interesting. Like we have cache channel, but we have decompress kernel. It's going to extract the kernel. So I'm not going to skip to there right now. What I'm going to do is I'm going to skip like the next, I'm going to skip the jump, okay? So I'm going to do right now, see where we have the jump here, where we affect. So here we see that this was like the jump that we had. This is like the next, this is the previous instruction, so I'm just going to jump to the next instruction, and I'm going to continue. And now look at this. So this is not relocated, and not relocated actually called decompress kernel. Now decompress kernel, as I mentioned in the x86 case, it's going to call like the relevant algorithm. In this particular case it's going to be a GZ, and do like all kind of things. And what we can see here is that under misc compressed c compressed misc.c, we have the decompress kernel function that will print uncompressing Linux and so on. Where will it print it? You need to have low-level debug for that to actually see it, okay? Like, because you still need like a very early console in order to take care of what is going on here. So there are all kind of tricks. You can define like debug so that you'll see like more things, so that you'll see the addresses and so on. We're not going to do it now. We're going to step forward. So now we are here in this decompressed kernel, and actually now the stack is more properly set because we're running on the higher addresses. So I can go ahead and do finish here, okay? And then I'll go to the very next command after what I add here. Just to prove it, if I looked at the current program counter -4, I will see that we are just after this. So we have branch and links. So if we do have like the branch and links, then we're pretty much good. So I can go ahead now and break, let's say, in the third one. I'm going to continue. Here we have two things. So I can go and step in, and you will see all kind of, again, cache functions and cache flashing functions and so on. I will not do it. I will just do next instruction this time and skip it. Then I have a very important call to enter kernel. Now I want to see what's going on here. So enter kernel is going to do a jump to R4. And this R4 is in the following address, 4008,000, which is sort of getting back because now we don't have these guys. Now I'm telling you from experience that there is another thing, because when we loaded the symbol files, we actually didn't even take care of this particular and interesting section, and it is a very interesting section. Now enter kernel is going to do something quite interesting. I want you to pay attention to that. So let's first let the address jump. This is where we are, and this is the code. Take a second to look at it. You can pause the video. And essentially, the idea is this. In enter kernel, we're actually going to execute the code from kernel head.o. So if I go and disassemble it, we will see other things. We'll see that like this address here is like 0 in section text, and somewhere we have id map.text, and we have init text, and this looks like promising. Turn MU on. I mean, it's probably something that we'll need. mmap switched, it's critical, but I will not do a spoiler. I'll tell you later. Like, I don't have everything, okay? And I have section head.text, and this code from this section head.text, it looks like what I'm looking for. So check it out, like hip stub install, we have MRS and then exclusive OR, and here we see like the same things, okay? Now, what I can also tell you is that if we look at the top tree VM Linux and we do an opt dump to VM Linux, then actually we have the same function, but it's in section head.text, and the addresses here are actually also different. So what I want to do, this is the proper VM Linux, what I want to do is to enable this section so that I will see it too. This is one thing. The other thing, pay attention here, it starts with C because it's after we have paging. And I also want to see where is like the section init, like in this process. So if I want to see where is the section text, sorry, then this is how it's going to be. In offset, 1, 0, and so on. So I'm going to do the following thing, friends. What I'm going to do is I'm going to reload whatever I'm doing right now. I'm going to first, just to be on the safe side, I'm going to get rid of all like the previous symbol information. I don't want remainders from compressed VM Linux, which was the previous file. So now let's see what is our current directory, pwd. I'm going to add symbol file, and I'm going to use VM Linux as is. I'm going to give it the offset that I saw. It started with C, but now I see that the address space starts with 4. So that is what I'm going to put. And for the section .head.text that we saw, I'm going to put the current one. And I'm going to say yes, that's what I want. I'm going to add a display, and voila, we have this, alright? So I'm going to skip this branch and I'm going to continue with what we have here. Okay, so according to processor type, we're going to execute other functions. We're going to let a tags. So what we want to see, we want to see where we have a jump. So we're going to just skip it. So th break to this one, cont. All right. So here is like the new next function, create page table. It looks like we're going to be close to actually have MMU enabled, which is actually also available here. So I'm going to skip this one. And for MMU enabling, we're going to have here, we invalidate L1 cache. It's going to take quite a while, so I'm going to go ahead and progress in it. I want to branch to LR, so that's what I can do. At this point, I can safely just do finish, and I will get back to the previous frame. But I'm going to play it safe. I'm going to, then we have like a branch to V7 set up. I'll do it also, why not? And then I'm back to turn on MMU. And here, look what we have. We're going to have this branch to mmap switched. And this is very important. Look what was the address space before and what is the address space now. So we can go and see that we step through it, and at some point that we step, we add like a branch, and we still again lose like debug information. And actually before things looked very promising in our way, we actually saw the branch to start kernel. We actually saw the branch to start kernel. So what we want to do at this time, we can say, okay, it was good, it was nice. We're now in MMU enabled mode. We can just use the debugging file as is. Yes, I will load it. The display after every loading is empty, so we're going to reconstruct it. Display slash, let's say, $20i $PC. And here we see that we are in MIO set. This will also take a while. So let's actually go ahead and get back from that. But the stack doesn't look so promising for us. So we want to actually do like the more manual thing, okay? So here we have like the branch, and then we have a pop to PC. So we're going to break here. We have the branch. You also need to like look at the code if you don't understand completely. You need to look at the code and like see where the branches may be. So here we are in mmap switched, okay? And we're very close to start kernel. Now, we don't have any jumps here, so we were expecting to actually go to start kernel, and this is the branch to start kernel. So when we do like this this stepping, we can now see that we have like everything that we would expect. And I'm just going to single step here. We have all kind of tracers. We have a call to print k. When you print something to print k, it prints to a variable that is called logbuff __ logbuff. So this is what we currently have here, like booting Linux on physical CPU. And I'm going to skip the print instruction. I will not see anything like on the console. But what I will do is see it here, and this is the banner, and then we can continue with our debugging. So I'm going to break in this guy. I'm going to continue, and then you can see that this function doesn't do all that much. It's going to actually, and let's do this slash, let's see, 20i PC. So it's going to call rest init, which is under this address, and here we are going to soon enough call kernel thread that will start like the kernel init. Like by this time we can examine how our kernel log looks like. Once again, this is a mistake, this is how you do it, and we see that we have like all kind of like messages here. And if I now continue, then we can see that our kernel continued executing. So this concludes our walkthrough. If there are requests, I can go on the more low level parts. And having seen that and having seen our very detailed explanation on x86, then you should be very comfortable in reproducing these steps, in teaching yourself in any possible architecture, in MIPS, in PowerPC, and you name it. So that would be all for now. And that's it. So let's go to the thank you slide. So that's it.